Hello, everybody. So we're still talking about the kinetic reactors in Aspen Plus, and now we will talk about one important concept that we need to understand well before we go ahead and start working with Aspen Plus, because there are many things that we have to input to the software that needs understanding of what we're going to talk about now. So what we're talking about is the reactor kinetics. So we'll understand what we mean by this word, what is the reactor kinetics, and we will kind of cover two kind of the most famous kind of kinetics, the power law kinetics, and the Langmuir-Hinchelwood kinetics, which is LHHW. This is kind of complicated and kind of long process to work with. So I'll keep this, or I'll not talk about this type of kinetics today. I'm gonna keep it after finishing the power law kinetics and solving the example on Aspen Plus, and then we will move to this, so that we don't get confused between both equations. So first, what is the kinetics? The kinetics is an equation that represents the speed of reaction, and it takes into account all the parameters that affect the reaction rate or the speed of the reaction. So by the speed of reaction we can, or to describe the speed of reaction, we can call it the rate of reaction, which is the change of concentration of reactant with time, or the product, whatever. If it's reactant, it's going to be negative dc by dt. If it's product, it's going to be dc by dt, or in the gas phase it's going to be dp by dt, which is the partial pressure. So the change of the concentration or partial pressure with time is what we call the rate of reaction. The factors that affect the rate of reaction are many. In cases there might be one or two, and in other cases there are more. We have the concentration of the reactants. Sometimes the concentration of the products affect the rate of reaction, the temperature, the pressure. There are many parameters that affect the rate of reaction. And this rate, either it is power law, if even if it's Langmuir-Hinchelwood, or whatever the kind of reaction that we are dealing with, there is a proportionality constant that is called the rate constant. It's an important parameter that we have to know. The rate constant is kind of represents how the factors are related to the rate of reaction. So you have many parameters, like as we said, the temperature, the pressure, the concentrations, and all these things, and they are related to the rate of reaction with, or they are proportional to the rate of reaction. The constant of, or the proportionality constant, is what we call the rate constant, which is the lowercase k. And it's important to keep in mind that this is a lowercase k. It's a small k, not a capital K or uppercase K, because the capital K is what we mentioned in the previous video, the equilibrium constant. So this is not the equilibrium constant, it's the reaction rate constant. I don't know why they use the letter K for both, but just to prevent any confusion, this is a lowercase and the other is an uppercase. The reaction rate constant, the lowercase k, takes the very famous form, which is the Arrhenius form, which is k equals k node multiplied by exponential of negative e over rt. And it can be rewritten in the linear form by taking the len or the log of both sides. Then it's going to be len k equals len k node minus e over rt. E is the activation energy, and it is kind of represents how easy the reaction can start. So it is the energy that's needed to start the reaction. So if the activation energy is low, then you don't need a lot of energy, so the reaction is easy to start. If it is high, then you need to put more energy to force the reaction to start. So this is in the units of energy per mole, or joule per mole, or any calorie per mole, whatever the unit that you're going to use. And the R is known, it's the universal gas constant. So this is the form of of the equation. There's one important thing that you need to keep in mind. If you take a look at this equation and see how the temperature affects the rate constant. Of course, if this increases, the K increases, then the rate of reaction will increase. This is very logical thing. So if you take a look about the temperature, you'll find it only in this term. So if this temperature increases, then this whole term will decrease, and this is negative, and this means that the K, the length K, and then accordingly the K will increase. So this is kind of universal fact that as you increase the temperature, as the rate of reaction increases. This is kind of very known thing. And again, just to prevent any confusion between the rate of reaction and the equilibrium of the reaction. So in case of exothermic reaction, increasing the temperature will increase the rate of reaction, but it will end the reaction early. So you will not reach high conversion because of the equilibrium concentrations is gonna be low. So you cannot get high concentration of the product, but you can reach this final concentration quickly because you are increasing the temperature. And that's why in exothermic reaction you might get kind of trade-off. If you reduce the temperature, you can achieve higher conversions, but you will achieve these conversions slowly. If you increase the temperature, you will achieve lower conversion but quickly. So there are kind of trade-off in exothermic reactions between the speed of reaction or the rate of reaction and the equilibrium conversion. So this is one thing to keep in mind. So in general, it's better to increase the temperature if you want to increase the rate of reaction, and then you can study the equilibrium conversion later. There was one other form of the equation that is kind of used in many cases, which is this form that is used in the presence of reference temperature. You are taking into account there is a reference temperature. The reaction is not calculated based on the absolute temperature. You are taking this with reference to a reference temperature, which is T node. So you can write it here. You can find the T node here and here. It's just one other form of the equation. I personally didn't see it in any way else but in Aspen Plus. So this is why I mention it here. You can use it if you want, and if you don't want to use it, just put T node equals, or just don't put any values for T node and N, and put N equals 0, and then it will end up with this shape. Anyways, so now let's talk about the equations. We mentioned that there are two models that we are gonna mention: the power law model and the Langmuir-Hinshelwood model. The power law is kind of the simplest form of the kinetics of the reactions. It takes the form R equals K multiplied by A power A and B power B. Just to understand, A and B are the reactants, and having them in square brackets mean that these are the concentrations. So this is the K multiplied by the concentration of A to the power of A and concentration of B to the power of B. So it is a function of the concentrations of the reactants. If it's a gas phase reaction, it's going to be partial pressure of A and partial pressure of B instead of concentrations. So these are the concentrations that are affecting the rate of reaction. In case of having a reversible reaction, then there is going to be K forward. This is going to be K forward, and then there is going to be minus K backward multiplied by the concentration of the product. So it's like having two different equations or two different reactions. So there's a reaction A and B going to C and D, and this is the equation that is representing the forward reaction, and there is the backward reaction, which is C plus D giving A plus B, which is the reverse of this reaction, and this is going to be K backward multiplied by A multiplied by B. So again, this is just a function of the forward or the reactants, or the concentrations of the reactants, and the powers A and B are called the exponents, this A and B. And this is why it's called power law, because it's the concentration raised to the power of A and the concentration raised to the power of B. Then you'll have as many concentrations raised to as many powers as you want. So these are the exponents, or sometimes they're called the partial orders of reaction. Usually let's say you have Ka only and you don't have this B, then this A, the lowercase a is called the order of reaction. So if it is Ka power 1, then it's the first order kinetics. If it's Ka power 2, it's second order kinetics. If it's power 3, it's third order kinetics, and so on. So in this case, you have more than one power. So this is called the partial order of reaction. So you would say that this reaction is, let's say A equals 1 and B equals 2 is first order in A and second order in B, to describe this equation. Or you can say the overall rate of reaction is 1 plus 2 equals 3. So its overall rate is, or overall power is, or order of reaction is 3, the third order. In case of dilute solutions or you have an elementary reaction, the exponents are the stoichiometric coefficients. So if it's 1A plus 2B, then A equals 1 and B equals 2. But again, this is for elementary reaction. And by elementary reaction, we mean that the reaction is only one step. Let's say you have a reaction A plus B goes to C, then it may go by just A plus B, or 1A reacts with 2B giving C, or it can reaction go in other way, like 2A plus 3B gives an intermediate product that reacts with A giving the final product. Then there are many reactions, and the final reaction that we have is the sum of all these reactions. In this case, it's not an elementary reaction because there are many steps that are included that we do not mention. But in case of elementary reaction, which means that the reaction that we mention is the actual reaction that takes place, there are no intermediate steps, then the A and B are gonna be the exponential, the stoichiometric coefficients. This is almost everything I want to mention about the model. But in the next video, we're gonna solve this example. It's kind of simple, but it's important to kind of understand it well, because it's gonna make us understand many things. First is how we can define the reactions in Aspen Plus. Second is where we put the variables, because or the parameters that we have, because it's kind of tricky, and how we can define a reactor and tell the reactor that you are gonna deal with this kind of reaction. It's kind of a nice thing to understand, because it's not gonna be as easy as it was in the ideal reactors. So this reaction that we're gonna deal with is the cracking of acetone. So this is acetone giving ketene and methane, and this is the rate constant, the Arrhenius equation of the reaction rate constant, and we have some information about the feed flow rate and the temperature of the reaction, the pressure, and we need to achieve 20% conversion, and it is in a tubular adiabatic reactor. So we will kind of combine many things here dealing with reactors and reactions, and it's kind of nice to see the outputs of the kinetic reactors compared to the outputs of the ideal reactors. So this is going to be the topic of the next video, inshallah. So I'll see you then. Goodbye.